Hello, my name is Chloe Arthid. I will be presenting on the effects of climate change and climate variability on central Idaho salmon populations. What first got me interested in this topic of research were the effects of climate variability on habitat requirements for specific species and those aquatic ecosystems it was involved in, such as salmon. I personally decided to take on this project because my father, David Arthid, has worked for over 15 years as a salmon fisheries biologist under NOAA, or National Oceanic and Atmospheric Administration, for the National Marine Fisheries Service, and is currently pursuing his PhD at the University of Idaho. I am majoring in environmental science with a focus in climate change, and thought the connection between the science I have heard growing up and never understood and what I have learned in both this class and others within my major would be interesting. Salmon are also a threatened species with sensitive and specific habitat requirements. So even seemingly minimal climate change shifts have larger habitat and population impacts. I am testing how climate variability and change can affect Chinook salmon populations and habitat conditions in the upper Salmon or Lemhi River. Salmon habitat requirements are considerably more sensitive than other species. If the water is high and cold in the seasons where there needs to be more birth and growth, the salmon will not have enough food or energy to live, let alone reproduce. If the water is hot and low, this means that the stream flow is slow. This makes the water stagnant, in turn influencing how much food is flushed into the salmon breeding grounds. In addition, they are forced to waste unnecessary energy on thermal regulation when the water is too cold or hot for them to sustain. However, the more ideal conditions for prime salmon survival and reproduction is for the air and water to be warm. This increases the growth of insects and the warm season increasing the growth of food resources. The water should be flowing high and fast. This help keeps the water cool and keeps food drifting past the salmon breeding grounds. When there are anomalies in climatological patterns from either climate change or natural variability, there are significant effects on salmon populations, and that is what I will be studying. I gathered temperature anomaly, and precipitation data for the Salmon KSRA climate station in Salmon, Idaho for the months April through August. I focused on the years 1987 through 2017. This was gathered from the West-wide drought tracker from the American Meteorological Society. I gathered streamflow data from the USGS Surface Water Monthly Statistics for Idaho. I used this throughout my report and the years within 1983 to 2017. I used the same months mentioned before, April through August. I used the Lemhi River NR Lemhi Idaho Station. This was all from the National Water Information System web interface for streamflow. I obtained the snow water equivalent data for all the years available, which were 1996 through 2016 for April through August. This was from SNOWTEL data on the Schwartz Lake Station near Salmon, Idaho. I used all the data was used from Natural Resource Conservation Service database. For population, which was perhaps the most difficult to find and to work with, I found from the Idaho Department of Fish and Game Spawning Ground Survey, and they are open to the public as well. And this is the Idaho Data and Apps website where you can find it. So once I gathered all my data, I started to compare temperature and precipitation on the metric system for those two between April and August for the years 87 through 2017. There's a lot of temperature variability and precipitation variability. However, there is a obvious negative relationship over the years that precipitation goes down. And I really wanted to figure out why that was or what was causing that. So next, I made a correlation between temperature and precipitation and found that there was a negative relationship for each year. So the lower or the higher the temperature, the lower the amount of precipitation. And so the lower the temperature, the more precipitation. And I thought that was an interesting, very, very significant relationship. And what makes a relationship significant is that the p-value is below 0.05. And I tested these after I ran the data sets for every data mentioned on the Correl regression in Excel to obtain the R value, and then inserted this into the website to test statistical significance from John Aboxiglu for the class, to determine a p-value, or as provided on the website to be directional probability, and it must be below 0.05 to be considered significant. And for this, it was very, very low. So for the next significant or scatter plot that I made to test significance, I put snow water equivalent on the x-axis by stream flow. So that resulted in a very positive relationship where more snow results in more stream flow, which is very obvious. And I just wanted to, make sure that everything was positively statistically tested as well. This also had a very significant p-value, very below 0.05. I decided to next test the anomalies and how the anomalies on either side of the temperature spectrum would affect stream flow. This came out negative as well. So as temperatures rise and get above normal and above the normal high temperatures, there is less water and less stream flow. Whereas when they are negative and colder on the spectrum, these are abnormal cold temperatures, there are higher stream flow levels. So how stream flow relates to salmon is a little bit more interesting to look at. Over the years, I first tested how pure red counts of salmon compared to stream flow, and I didn't find anything significant, and that was disheartening. And then I plotted the data on a time series and realized that there was just a delayed response based on generational patterns. So as you can see, every few years after a stream flow anomaly or rise or a sink, there a few years later is a population of salmon rise or sink. And this has to do with their 4-year life cycle. They live about 4 years and spawns between 2 and 4, and then they die. So these delayed population dips are from salmon generations that were unable to replace themselves due to optimal stream flow. So as you can see here, beginning with the eggs to alvin, fry, par, and smolt is when they begin to come back in that 1 to 2 year range to spawn, and then up to about 4 years is when they generally die. So that is when the generation about ends, and then their children take over the next generation of the next 4 years. And this can be explained through 4PI, which was data that I gathered, or from the data set I gathered. And it is stock by recruit productivity over 4-year intervals. So every 4 years, the stock is divided by the recruit, which is what comes back. The recruit is what comes back to the breeding grounds. And I took the August biannual stream flow per cubic feet per second, and averaged every 2 years of August, because August is the harshest month. There is the least amount of stream or water stream flow, least amount of precipitation, and the highest temperature. So that is hardest on the salmon, especially for reproduction. And there was an extremely significant relationship between the raise in stream flow from earlier snowmelt and precipitation than low stream flow where there was high mortality in salmon populations. I then wanted to look at how normal climate variability had an impact on long time salmon populations. I observed every 10 years there was a drop in population in the stock recruit ratio over stock years. So, that's every however many years that they stock them. And you can see that there are significant declines. And those declines correlate or match up with these um, Pacific Decadal Oscillation Index values that happen every 10 years. And salmon populations are in tune with these and reacting to these 10-year climate variations that produce harsh climate for salmon to survive in. This graph, which is stream flow on the x-axis again, and the 4 generational red counts on the y-axis, provide a very significant relationship. It signifies the extreme significance between stream flow increase and salmon population increase. If the stream flow is below 1, the stock salmon are not able to replace their population numbers. As stream flow rises, however, you can observe in the 6,000, 7,000, 8,000 stream flow range, the salmon populations are able to double, which would have been at 2, to even triple their populations. So that is very strong evidence that the higher stream flow, the higher populations of salmon there will be. And to conclude, I have found throughout the tests conducted and research done that climate has a significant effect on Chinook salmon populations. I found that as temperature rises, precipitation decreases, and salmon populations are negatively affected due to stream flow shifts. Stream flow is affected by how early the snow melt season begins and how long the warm temperatures last. If the warm temperatures are too high, then this can affect the habitat requirements. For example, raising the temperature of streams and lowering water levels due to evaporation. To put it simply, and to quote my father, fish need water. So if stream flow is lessened, so are salmon populations. Thank you.